Hello, good morning, good evening, good afternoon, students. Thank you for tuning in to Chemistry with Ms. Hernandez and fifth period. Today we're covering section 5.1, Electromagnetic Spectrum, and all of this information comes from your packet on ck12.org. Okay, today's topic is electromagnetic radiation. There are 7 types of electromagnetic radiation. You have to remember, you start off with these big waves and then they get smaller and smaller and smaller. The smaller they get, the more dangerous they become. Okay, remember, it is the same thing that you see here. What are waves? What are waves? Oscar's not here to help me. Who's helping me? Irvin or Alexia or Melissa? Who's helping me with the introduction today?
Waves can come in many sizes. Here we see a large wave crashing on the beach. Other waves can be very small and regular. We normally think of waves as being made of water, but they are forms of energy that take on the characteristics of waves. The idea of a wave has played a major role in our understanding of how the atom is put together and why it behaves the way it does.
All right. So all of us, thank you, Alexia. All of us have gone to South Padre Island and we've seen the waves crashing as they come in to shore. And the further out you get, the bigger the waves become. The closer you get to shore, the smaller the waves become. And think of those large waves in the deeper end as being those radio waves. They're a lot bigger, a lot longer. And think of those smaller waves as you get closer to shore being those gamma rays that we're talking about on the other end of the spectrum. Okay. Big waves, okay, they're okay. You can be exposed to large waves of electromagnetic radiation. Small electromagnetic radiation, smaller waves, those are the dangerous ones. Okay. And let's continue. All right. So we're going to start off by talking about properties of light. They start to discuss Rutherford's atomic model. And you've probably seen this picture in books or even in commercials or even the TV show Big Bang Theory, right? But this is Rutherford's version of the atomic model. So, the nuclear atomic model proposed by Rutherford was a great improvement over previous models, but it was still not complete. It did not fully explain the location and behavior of, of the electrons in the vast space outside of the nucleus. In fact, it was well known that oppositely charged particles attract to one another, right? So what we know right now is anytime I have a positively charged atom because it lost electrons, and anytime I have a negatively charged atom that gained an electron, there's going to be an attraction that usually brings these atoms together. So when Rutherford came out with his model, it was really good. It was a lot better than any other model that had been proposed by other scientists. So, it was great, but there was still some questions about it. So Rutherford's model did not explain why electrons don't simply move towards and eventually collide with that nucleus, okay? And the reason why people were wondering that is, well, because we know that electrons, as they orbit around the nucleus, well, they have a negative charge to them. And that nucleus has protons that have a positive charge. So people always said, well, why doesn't this electron that's rotating around the nucleus get attracted to it and collapse the atom? Okay. That's what people were trying to figure out. And they kept asking Rutherford, right? Because he did have the best version, the best model of what, atoms look like in his time. So experiments in the early 20th century began to focus on the absorption and emission of light by matter. These studies show how certain phenomenon associated with a light revealed insight into the nature of matter, energy, and atomic structure. So, what they're talking about there is they started to do research about when light hits an atom, right? When light hits an atom, it doesn't actually hit the atom or the nucleus itself. It actually hits the electrons that are orbiting outside of that nucleus. And what usually happens when energy is absorbed by these electrons is, well, you have an electron in, what if you have an electron in energy level number 1 as it's going over and over, right? Well, if light hits that electron, it will jump to, if it's an energy level 1, it'll jump into energy level 2 with a larger orbit, right? Because it's highly energized. It's got that extra energy it needs to be in energy level number 2. But the only thing is that that electron cannot hold on to that energy. Eventually, that electron has to release the same energy that it absorbed. So, what usually ends up happening is that that electron will release the energy, and as it releases the energy, it's going to fall back into its original energy level, which in the case of our example, energy level number 1. Okay, so it's an energy level number 1, and it's rotating. It light comes in, hits it, it jumps to energy level number 2, which is a larger orbit, and it could probably stay there for a little while, but it cannot stay there forever, because eventually that electron will release the energy and will go back into its original smaller orbit. Okay, because it does have enough energy to stay in that one orbital. All right, so here you have Rutherford's atomic model. You have in red and black, you have your nucleus, which are your protons and your neutrons, and then in blue, in the blue circle around the nucleus, you have your electrons in that cloud, and these black circles or ovals that you see here are the orbits where the electrons are doing that rotation around the nucleus. Okay. All right, students who are live with me and students who are watching, is this statement a true or false statement from the previous slide? All right, so did we just talk about this? True or false? Rutherford's model did not explain why electrons don't simply move towards and eventually collide with the nucleus. Okay. Rutherford's model did not explain why electrons don't simply move towards and eventually collide with the nucleus. So basically, why doesn't the atom collapse, right? Did he not explain why? Okay. Did he answer that question? True or false? Is that a true statement or a false statement? What do you remember? Rutherford's model did not explain why the electrons don't simply move towards and eventually collide with the nucleus. True statement or false statement from the last slide? Only one person has answered. Come on, guys, take a guess. Is it a true statement or a false statement? What do you remember? Did Rutherford explain why electrons don't fall into the nucleus? Did he not explain that? Or did he? True or false? I need a little bit more responses in this, guys. A little bit more responses. Maybe one or two more. I got 5 people in the pair deck, and only 2 people have answered the question. True or false? Rutherford's model did not explain why electrons don't simply move towards and eventually collide with the nucleus. All right, 3 responses is enough for me. That is a true statement. Yes, yes. Rutherford did not explain why electrons don't fall into and collapse the atom. Okay? He did not explain that. That was the reason why people started to do studies in the early 20th century. The nature of light. Okay. In order to understand the nature of of the electron, we first need to look at the properties of light. Prior prior means before, right? Before 1900, scientists thought that light behaved solely as a wave. Okay, as we will later see, this began to change as new experiments demonstrated that light also has some of the characteristics of a particle. First, we will explain the wave-like properties of light. Visible light is okay, so here we have a picture of the electromagnetic spectrum. It might not be what is shown in your packet, but it is a good one. It shows the seven different forms of electromagnetic radiation. And remember, on the left side you have the non-harmful electromagnetic radiation. On the right side, this is the dangerous side. Okay, you get exposed to too much gamma rays, you can get cancer and eventually you'll pass away. Or if you get exposed enough, your organs will just begin to shut down because they cannot handle too much exposure. Okay, so first off, very long waves is radio, and then they get shorter for microwaves, then infrared, then visible light, then UV, then X rays, and then gamma rays. And remember, radio waves and TV waves, that's how your antenna connects to that radio station, and you are able to listen to your favorite station, your favorite music. Microwaves, anytime you heat up your food in the microwave, that is, you're using a form of electromagnetic radiation. And then here you have infrared light. Infrared light is like when you have those night goggles on and you're able to see people at night. Then you have the visible light spectrum. This is the only part of the spectrum that you can see with your eyes. UV light is the energy that comes from the sun. Too much can give you a really bad skin burn. And then X-rays. X-rays is when they take a picture of your bones because they think you might have a broken bone somewhere. And you cannot get exposed to too much X-rays, or it can scramble some of your DNA, especially in your reproductive system. Gamma rays is what nuclear bombs are all made of, and Hiroshima, Nagasaki, all of those were nuclear bombs that dropped, and gamma rays is what came out of them. Visible light is one type of electromagnetic radiation, which is a form of energy that exhibits wave like behavior as it moves through space. And remember, there's two types of waves, there's the vertical electronic wave, and then there's the horizontal magnetic wave. And both of them, I can't even do it, right? You got this one, and then you got this one. I can't do them at the same time. It's weird. Other types of electromagnetic radiation is the dangerous gamma rays, the less dangerous X rays, and then you get into ultraviolet, visible light, infrared, micro, and radio waves. The figure on top shows the electromagnetic spectrum, which is all forms of electromagnetic radiation. Make sure that you notice that visible light only makes up a very small portion of that entire electromagnetic spectrum. All electromagnetic radiation moves through a vacuum at constant speed, which is 2.998 times 10 to the 8th meters per second, while the presence of air molecules slows the speed of light by a very small amount. All speed of light moves at 3 times 10 to the 8th meters per second. It's fine, Alexia, don't worry. Okay, so that's like saying 300 million 300 million meters you're passing 300, you're traveling 300 million meters per second if you are light. Okay, so that's how come some people say that some of those stars that you see up above might not actually be there, because we could be watching the past. Okay, we can be watching the past because those stars are so far away that maybe they have they have exploded or died, but since we still see that light coming off of them, uh, we still consider them, or we can still see them shining bright, especially at night when you're out of the city. All right. Your second question, okay? Your second question. And remember, if you're not in the pair deck, you should still be able to chat in or to post in the Google Meet chat. All right, your second question, and this is a typing question. It's asked you to list two types. I'll settle for one type. Two types of electromagnetic radiation discussed in the previous slide. Tell me two examples of electromagnetic radiation that is in that spectrum that we just talked about. Okay, and the reason why I went over it twice is because I knew this question was coming. I was trying to get you guys to at least remember one or two of those and get it stuck in your head so that you can remember it for this slide. Okay, so tell me two examples. I will settle for one example of types of energy on that spectrum. Okay. How are we doing? Nobody has responded yet. Anybody want to just come off mute and tell me one of those types of electromagnetic radiation? Anybody want to come off mute and just tell me that instead of having to type it out? What's one of the ones that we just talked about when we go and we listen to 104.1, Wild 104? Or tell me, what do doctors use to verify if you have broken bones? Or you can tell me what type of energy was in that atomic bomb that we dropped on Hiroshima. Anybody remember any of those, any types of electromagnetic radiation? Only one person has answered. What do we use in order to heat up our food? Remember that one? What do we use to heat up our food? Or what type of energy comes from the sun? Anybody remember that? What type of energy comes from the sun? All right, we got two responses. Let's see what they put. Radio waves and microwaves. Yes, that's the less dangerous part of the spectrum. Very, very good. What type of waves uh, come out of those nuclear bombs? Anybody remember? Oh, so sorry. Anybody remember what type of energy was dropped on Hiroshima? Anybody? And nobody remembers that one? Gamma rays. Gamma rays. Gamma rays are the dangerous stuff. All right, so the figure to the right shows the electromagnetic spectrum, or how the electromagnetic spectrum displays a wide variation in wavelength and frequency. So, radio waves, remember, radio waves are as long as those buildings in New York City and maybe even longer. I think in the video it says it's as long as the earth. Um, so anytime you have very long waves, um, that just means that how many pass in 1 second is frequency. Okay, frequency is like how often those waves pass in a series of time, and that series of time is usually 1 second. All right, and when it comes to radio waves have long waves. So when it comes to frequency, frequency is considered to be low. Okay, if you are a gamma ray, you have very short waves. Okay, you can pass a lot of them in a short period of time. So when it comes to frequency of gamma rays, frequency is considered to be high. Okay. Now, what's your favorite radio station, Irvin? If you went to your car right now, what station would you turn on? Irvin, are you there? Okay. Anybody? Melissa, Alexia, Caitlin. What radio station do you like? Okay, Alexia likes 107.9.
104.9.
104.9. Okay, did you know that that station, anytime you turn on the radio and you turn on 107.9 or 104.9, that's the frequency for that station. Did you know every single time that you listen to 107.9, that's how many waves are passing every second that you're listening? Did you ever think about that? That's the frequency. That's what you tune into in order to get to that radio station. So that means 107 waves are passing for every 1 second that you listen to that radio station. For Irvin, it's 104.9 waves are passing every second that he's listening to that radio station. Isn't that crazy? Did you ever think about that? Probably not, right? But you're thinking about it right now. Yeah, that's crazy. When I started reading about this section, I was like, wow. So 94.1, the rock station, I'm listening to 94 waves passing every 1 second. That's crazy. The electromagnetic spectrum encompasses a very wide range of wavelengths and frequency. Visible light is a very small portion of the spectrum with wavelengths from 400 to 700 nanometers. Okay? 400 to 700 nanometers. So, the one thing that I want you to remember from this slide is when you have long waves, frequency is low. Anytime you have short waves, frequency is going to be high. Okay? So here you have your visible light. Visible light, anytime you step out into the sunlight, you can probably um if you're using a glass prism, you can spread out the light and see that visible light spectrum, right? You can get light, shine it on a prism, on a glass prism, a glass triangle like you see here. You can bend the light so that you can see the colors of the rainbow. Okay? So I don't know if you've ever like gone into your vehicle and like there's some light coming in and all of a sudden you see a little bit of rainbow in your vehicle. That's because the glass that the sun is shining on is bending the light so that you can see those colors of that rainbow. Okay? Um it says here yielding. Okay, so anytime you bend that light, you're yielding that visible light spectrum. Red light has the longest wavelength and the lowest frequency. Anytime you see violet light, violet will have short waves and high frequency. And again, they tell us about how long these waves for the colors are: 400 to 700 nanometers. Okay. And then for the picture, it says a small beam of white light, which is the sunlight, is refracted. Refracted is just a fancy word for bending light as it passes through a glass prism. The shorter the wavelength of light, the greater the refraction. So light is then separated into the colors of the rainbow. All right, you got one question. Do you agree or disagree with this statement? The longer the wavelength, the higher the frequency. Is that true? Did I say that the long waves give high frequency? Do you agree with this statement or do you disagree? Do you agree or do you disagree? Okay, tell me what you think. Tell me what you think. You agree. Melissa says she's agreeing. So she says that long waves give a high frequency. Anybody else have a different answer for that? All right, let's see what they said online in the Pear Deck. Yeah, Alexia says that she disagrees, and two other people say they disagree. Be careful, Melissa. Be careful. Long waves, remember, if you have a long wave, it's going to have lower frequency because it's going to take long for you to go up and down, up and down. So how many waves pass in 1 second is considered low for long waves. When you have very short waves, they're very small, right? They're going to go up and down real quick, up and down real quick, up and down real quick. Then that means that you can have a lot of small waves passing in 1 second. Frequency is high. Okay, be careful with that, Melissa. All right, here is the video. You're not going to be able to see it in Pear Deck. It's going to take me to YouTube. Okay, so guys, come back to the Google Meet so you can see. Come back to the Google Meet so that you can watch. I need to download some of these so that we can skip all these ads.
Light is the connection between us and the universe. Through light, we can experience distant stars and look back at the beginning of existence itself. But what is light? In a nutshell, light is the smallest quantity of energy that can be transported. A photon, an elementary particle without a real size that can't be split, only created or destroyed. Light also has a wave-particle duality, being kind of a particle and a wave at the same time, although this is a lie. Also, when we say light, we actually mean visible light, which is a tiny part of the electromagnetic spectrum, energy in form of electromagnetic radiation. Electromagnetic radiation consists of an enormous range of wavelengths and frequencies. Gamma rays have the smallest wavelengths because they're the highest energy photons, but most gamma rays are just under 10 picometers, which is still way smaller than a hydrogen atom. For reference, a hydrogen atom compared to a cent is about as big as a...
So those gamma rays are so small that it's smaller than the smallest atom that we have. Okay? Gamma rays are smaller than the smallest atom on the periodic table. That's how small they are.
Cent compared to the moon. Visible light is in the middle of the spectrum, in the range of about 400 nanometers to 700 nanometers, about the size of bacteria. On the other end of the spectrum, radio waves can be up to 100 kilometers in diameter, while the biggest wavelengths we know exist can span from 10,000 kilometers to a baffling 100,000 kilometers, way larger than Earth. From a physics standpoint, all these different waves are the same. They all have the wave-particle duality and travel at c, the speed of light.
So here you have the different sizes of these waves. Over here is like what you have radio, and then you have over here the visible light, and then you have the small waves of gamma.
Light, just at different frequencies. So what makes visible light special then? Well, absolutely nothing. We just happen to have evolved eyes that are good at registering exactly this part of the electromagnetic spectrum. This is not a complete coincidence, though. Visible light is the only set of electromagnetic radiation that propagates well in water, which happens to be where most eyes first evolved millions of years ago. That was a smart move because light not only interacts with matter, it's also altered by it and can be used to gather information about the world around us with almost no delay, which is arguably really helpful for survival. Okay, where does light come from? A vast range of electromagnetic waves are created when atoms or molecules drop from a higher state of energy to a lower one. They lose energy and emit it in the form of radiation. At the microscopic level, visible light is created when an electron within an atom, that is, in an excited state, drops to a lower energy state and loses this excess energy. The same way incoming light can elevate an electron to a higher state of energy by being absorbed by it. Macroscopically, the moving charge of the electron creates an oscillating magnet field, which creates an oscillating electric field perpendicular to it.
So this is that double wave that I was talking about, where you have the electric field going vertically up and down and the magnetic field going side to side.
These two fields move themselves through space, transferring energy from one place to another, carrying information about its place of creation with it. Why, of all the things in the universe, is light the fastest thing there is? Let's change the question. What is the fastest way to travel through space in the universe? It's c, exactly 299,792,458 meters per second in a vacuum.
This is the speed of light that we're talking about. 300 million meters in 1 second. That's like anytime you watch like Star Wars, that Millennium Falcon, when you see it turn into light, they're supposedly moving at the speed of light, which is 300 million meters in 1 second. So anybody who can create an engine or a jet or something that can travel at that speed with humans will become famous, rich, anything, and they're gonna give the humankind and the human race advantages that we've never ever had before. Imagine traveling across our solar system, in a fraction of what what it would take now.
1 billion kilometers per hour. Electromagnetic radiation just happens to move this fast. Any particle that has no mass travels at c, without acceleration or any in between. The light that's being released from a candle does not speed up until it reaches light speed. At the very instant of its creation, its speed is c. So why is c, or the speed of light, finite then? Well, nobody knows. Our universe is just built this way. We don't have a smart answer here. So light is a part of a spectrum, an elementary particle that also behaves like a wave, propelled by two perpendicular fields traveling at the speed limit of the universe. Okay, that's nice and all, but what about all the crazy stuff about traveling at the speed of light and time, the twin paradox, quantum stuff, and things like that? We have to save them for another video. For now, let's just be happy that we evolved eyes that pick up waves.
Yeah, and definitely ask your physics teacher when you get that. Maybe he can give you a better answer in terms of time and all that good stuff. All right, so we are done with Perdick. In summary, electromagnetic radiation is a form of energy. Visible light has wavelengths from 400 to 700 nanometers. The speed of light in air is 300 million meters per second, also known as 3 times 10 to the 8th. Your review questions are very easy. What did Rutherford's nuclear atomic model not explain? Prior to 1900, what did scientists believe about the nature of light? What is visible light? What is the range of wavelengths? All right, let's see how many we can answer. Let me stop this.